Okay, so thank you for offering to be the chair. And actually, it's a great pleasure to be here, to attend this great workshop. And I'm very grateful to the organizers to make this possible. Today, I will talk about some results with my PhD student, Mr. Xinwang, about the entanglement manipulation. Essentially, we provide some new SDP bonds, and we show some irreversibility of this PPT entanglement manipulation. So my name is Runyao Duan. I'm from the University of Sydney Technology, Australia. So I traveled about 26 hours to be here. And we have a new center for quantum software and information. As far as I know, this is the second research center in the world with the name of quantum software. So you're welcome to visit us. We're working on most important theoretical aspects of this quantum computing. So you're welcome. And here is my student, Xinwang. So if you are interested in details, you can find the result from, talk about from these papers on archive. Actually, most of them already published, but I think this is the most easy way and free way to get the paper. So, so I think I can almost can skip this slide because it's just to give you, some basic notations what we will use. So, BHD, I think bodied linear operators, and also this if we have a set of state, then we can use this convex or use this notation. And we use the partial transpose. So essentially, if you have a bipartite system, so if you just want to take a transpose of one system, then we can use this this notation. So like TB, XTB means that we take the partial transpose of the system B. So we always have any sort of bulb. So we take the transpose according to bulb, and then we have separable state. And we use SEP to represent all separable states. So this S just the product state and the PPT state. So it's both X and XTB are positive, and the trace is 1. So separable state is a part of this PPT state, and we also use a bipartite quantum operation. So this is a CPTB map over this bipartite operation space, but E is separable if the Choi matrix of E is separable. That's the simplest way to define this, this separable operation. So we just consider the Choi matrix, and if its Choi matrix is separable according to this any small partition, then it's a separable operation. So similar, we call it a separable PPT operation if the Choi matrix is PPT. Okay, so that's the basic definition we use. Now we come to the the key topic of this talk. So we talk about the entanglement measures. So for this entanglement measure, we are most interested in two processes. So the first one is about the entanglement distillation. So we know that maximum entanglement states are very useful. So for many tasks, we need this maximum entanglement state. Of this very special form, phi k. So it's k by k maximum entanglement state. So the entanglement distillation is one way that we can distill a mixed entangled state into some copies of this maximum entangled state. So it's some way we transform some noisy resource into some pure resource. So this is a very natural way. So it's entanglement distillation. So for this way, what we do is we consider we use different class of operations. The most natural class of operation is LOCC. So we use local operation on the classical communication because this is physically feasible if we have any bulb in distant lab. But we also use this separable operation because this LOCC class, sorry, it's too high. So this class LOCC is actually it's very natural and physically relevant, but unfortunately it's also very complicated. So the structure of this class is not known so far. So what we do is normally we just want to have some some upper bound or some some other, Noah bound. So in this case, we use a nodule class called separable operations. So, or even, even sometimes we even just consider PPT, because even this separable class is very difficult. Mathematically simple, but when you actually do some calculation, you find this separable class is very, very, very difficult. This is why we have so many people to work on this separable issue.
For the distillations, the set and the PPT property have to do with the action on the bipartite system.
Yeah,
it's
yeah.
not the same that you had before.
So this is why I say I use this one. See? So we see so it need to be tricky. Yeah, I just I need to be lazy. So yeah, so we all can say bipartite system, and distillation we can eventually use some some measure called entanglement distillation (ED) to characterize what is the optimal rate we can have from a mixed state rule. So it's this the ED rule, okay? And the operation we use is PPT. So we say PPT assisted. And sometimes we consider a different process. This process is a little bit weird, but it's still very natural. So this is called the entanglement dilution. So the idea is we want to prepare a noisy state rule. But so we ask how many EPRs or how many maximum entangled state we need to prepare this one. So this seems a very weird process, but sometimes still useful. So because if something is too pure, then maybe you can't use it directly. You have to dilute it's in some way, and then make sure you can actually take it. So okay, so this is something we call entanglement of cost. So it's essentially it means how many EPRs we need to prepare a noisy state. So these are actually the two different process. And now because here we are most people here are mathematicians, I guess. So we need to make sure we are actually define something in some mathematically precise way. So this entanglement distillation can be defined in this horrible way, because it's actually you have to use this limiting procedure to define this. So it's just mean that if you have n copies of this state, and then you want to transform it into like a 2 to Rn copies of this EPR state, and you want to use this limiting procedure to make sure the approximation is good enough. So because I can't get into detail to express definition, but just make sure that this will be the precise way to define this entanglement distillation of state rule. But you can see actually this one is very, very difficult to handle with in practice. So especially here we have this LCC class. So as I said before, we use maybe separable state or a separable operation or PPT operation to simplify this procedure, the difference here is we just replace this class by PPT, okay? But still, it's still very complicated. So we don't actually use this definition in the following discussion, but I just want to give you some sense. What's the difference between information theory and operator algebra? For in most cases, operator algebra, people can say just a one shot. So one shot means I just have one operation and then I discuss the properties. But in information theory, what we need is we always have, we just have maybe one state, but we need to consider the, the asymptotic property of this state. So like here. So the state could be just 3 by 3, 2 by 2, but it's very simple state. But then we actually discuss the information theoretic property of this state. Then it could be extremely complicated. So this is why even for 2 by 2 state or 3 by 3 state or maybe other very low-dimensional class of states, we don't actually know how to calculate these quantities. Okay. So what we could do, on the one hand, these measures are very important because it actually captures the practical property of this entanglement, this resource state. And but on the other hand, this calculation is very, very difficult. So what we can do? So we have to relax our, our goals. We don't expect we can give the analytical form of this, but instead we want to have some upper bound, good bound. Okay, so this is why we consider just the bound, but not the actual, formulas. So how to, how to evaluate this is definitely very difficult. So we don't know how to do that. So instead, people are working on some some feasible way to upbound the entanglement. So this is very maybe one of the early quantity discovered by Vidal and Luna here. They have this logarithmic negativity. It's a very simple way to do it. You just take the state, and then you take the partial transpose, and then you use the trace norm, take log. This will be some quantity, very easy to calculate. And then it will show that this one was actually an upper bound of this distillation, entanglement distillation. So this is maybe the upper bound, the very feasible upper bound we have. And this have very many nice properties. We will see later, but I will say this have many many interesting properties, and it's before our work. This is probably the best known and the most computable upper bound for this ED. Okay, so ED is actually very difficult to calculate, right? Let me remind you again and again about this because it's really difficult. So this has been for a long time. It will be very good result, very good bound. But this quantity not just upper bound because it also have other properties like some entanglement monotone, like for instance. So other people also introduce this, this number, but that is a different, different purpose, not directly related to this entanglement of distillation here. So what we do is we want to find some tighter, upper bound for this entanglement of distillation. So one way we do is we just generalize this, the previous logarithmic negativity. So the way we do is we take we just use the same formula, except we use a variable x. But x has this constraint. X should be larger than or equal to rho AB. So you see that if x equal to rho AB, then this formula gives you the logarithmic negativity. But if they're equal, but if they're not equal, right? Then if you take minimization, then there is a possibility it could be strictly smaller. Okay, so this is actually the case, and we can write out the dual SDP of this number. So they are actually by the strong duality they are same. They are same. But with this formula, we can prove that very easily show that this new quantity has a number of interesting properties. For example, they are multiplicative. They are additive under this tensor product, and also it is the upper bound for this PPT distillable entanglement. So we have this ED next the EW. So let me briefly mention how we prove this. The idea to prove this kind of property, so additivity is normally very difficult. But if we can show some quantity can be right away of this SDP, then we can use this duality theory to prove it. So for example here, if you want to prove this one is less than or equal to the sum of these two, then we use this primal SDP. But if you want to prove that this one will be larger than or equal to this one, then we use this dual SDP. And then, they are equal, right? Because you can't have this simultaneously hold. Okay, so that's the idea. And if we want to prove this ED less the EW, then we have to use this dual SDP. So, but I just ignore details because that's not difficult. And then it's also detecting PPT distillable entanglement. So this EW is positive if and only if ED is positive. Okay, and it also has property that's non-increasing average on the PPT operation, and of course also LOCC operation. And this is the most interesting property probably we have because we can show that it's not more than this En. So that means sometimes this inequality is strict. Actually, in most cases, it's strict. So it's that if it's strict, then it means it's a better upper bound. And I want to see this En, as I said, right? It has all, it has a number of property. So all these property except this one. So this is why this EW of the En is actually very similar, and the EW probably is a very natural generalization of this En. Okay, so we can have some class of state like 2 by 2 qubits here, and then we can calculate this En and the EW, and we find that for many cases, this EW is strictly less than this En. Okay, but unfortunately even for this case, we don't know what is the value of this ED. So because ED is too difficult. Okay, and also there is another class. We can actually show that for this class, a new class of state 3 by 3, we can show that ED and EW is actually equal. They are equal, but they are strictly less than this En. So it's a very special state. Okay, so this is the first result I want to discuss. And now we want to see the, because we just now we only have the upper bound, right? We have upper bound for this ED. But in practice, we definitely need to have some lower bound. Because if we really want to prove some, some tighter result, then we need to make sure that we have upper bound and lower bound they actually match. So the one way we provide this lower bound is use a very special type of protocol. So we consider about this a deterministic entanglement distillation. So what we do is we don't allow any error, but we require the distillation is precise. So here is the idea. Here is the idea is what we do is for a given state rule, and what we do is we consider the maximum k such that we can find a PPT operation that can transform this state into a maximum entangled state. Okay? So for example, if k is equal to 1, then we can always do it. So because k equal to 1 means it's a product state. So you can, of course, you can transform any state into a product state. So, but here, the most interesting thing is we need to take the maximum. So in this case, what we do is, what we have is we have some quantity called the one-shot deterministic entanglement distillation rate for this state. And then this is a very routine trick in information theory. We take the asymptotic case. So we take n copies, and then we take the average. Then we have something called the deterministic entanglement distillation. Okay, so this is the very interesting property, quality. And so we have to see that this quantity is very easy to calculate because this class operation is PPT. So we can actually find a SDP, to calculate this number. The form is very simple, right? I don't want to get into detail, but you can see it's a very simple property. And the most interesting thing is the constraint is some interval. So it's an operator interval. So you consider operator interval, and then you take this maximum quantity. So it's say, and here P is the projection of this support of rho AB. So that means for this deterministic distillation, the only relevant thing is the projection of this support, but not the actual operator. So we have this kind of thing. So this EW is the upper bound we just introduced, and this ED0 is the deterministic entanglement distillation rate. So we want to calculate this ED. What we do is we always, we want to calculate this one and this one, and if they match, then we have the result. So this is why even the problem is extremely difficult, but for a certain case, we can still find the exact, number of this ED. Okay. So that's some result. But now I come to the key result we will have. So the result is about the risk bound, because risk bound is introduced by Eric Reins in 2001, and also studied by this Runyao and his colleagues. So this R rho is defined as the minimum of this relative entropy between rho and sigma. And sigma is a special class of states. It's positive, of course. And actually, it's not a state. It's just a positive, and they satisfy this property. So the partial trace of sigma takes this absolute value, and then the trace should be less than 1. So this is another way to write this respond. The original formulation of this respond is not in this form. So this nice formula, I think it's appears in this paper. Okay, so it's so once we have this, what we do is the risk discovered. This bond is an upper bound of this ED. So please see here. You see this one is not a SDP. It's some formula. It's some formula. Maybe we actually can have some algorithm to calculate this, but it's not SDP. So that means it's it's not easy. It's very complicated to calculate actually, but at least it's something we can calculate. Okay, so it's upper bound, and so this is one thing. Another thing is about this relative entropy. Okay, relative entropy is very similar to this risk bound. So you can see it's almost same, except here we take the minimization over this rho and the sigma is PPT state. So they are very, very similar. So you can see that this class is much than this one. So this is just a subclass of this. So that means this relative entropy, so this risk bound is always smaller than equal to this relative entropy. Okay, and so this routine trick in information theory, we always want to take this asymptotic regularization to make sure we have some better bond, or better quality. So this is asymptotic relative entropy. Okay, so we know that for this these two quantities, they look very similar, but they are actually not the same. We will see. So these two quantities, they are equal for 2-qubit state or 2/n state. So that means if one system is qubit, then this risk bound and this relative entropy are equal. Okay. So there are actually two unknown things. The first one is a conjecture. So in this paper, it was conjecture this risk bound probably always additive, because for the cases we know it's additive, and even for some very non-trivial cases we know it's additive. So it's very natural to conjecture maybe it's always additive, right? And also there is another open problem is whether this risk bound is always equal to this asymptotic relative entropy of entanglement. So as we see, the risk bound is very similar to this relative entropy, and but unfortunately people already know that the relative entropy is not additive. So how about if we take the regularization? Maybe after that it's definitely additive, right? According to the same copy, it's additive. So how about the relation between this risk bound and this this asymptotic relative entropy? So what we have is we have for 2-qubit state, we can have 2-qubit states such that risk bound 2 copy is strictly less than 2 times 1 copy. So it's not additive. That's the first thing. The second thing is for relative entropy, even you take the regularization, so it's asymptotic relative entropy is still strictly less than risk bound. Okay. So here the interesting part is this is 2-qubit state. Okay, 2-qubit. So that means these conjectures are not true even for this 2-qubit state. So the idea we show this is I just outline the ideas, prove ideas. So what we do is for 2x2 state we can explicitly construct a PPT state, such that this risk bound and this relative entropy are all equal to this relative entropy between rho and sigma. So this is a technique in actually these two papers. They all have this have this idea. So here is it's a little bit different. If we give you a state rule, then how to find a sigma such that the relative entropy is just equal to this relative entropy between rho and sigma. That is something very difficult to do. But now consider the case that giving you a sigma and then find some state such that the relative entropy of this state rho is equal to this relative entropy. That's something you can do. I mean, so that's a little bit different. Otherwise, you probably find nothing new here, right? But that's the new, something new, okay? And then what we do is we find some upper bound for this relative entropy, but for two copies. For two copies, we find the upper bound for this. But this is the algorithm developed in this people's paper. This paper has a neat problem. So the algorithm had a neat problem, and it was fixed in this paper. So we're lucky, right? So this is why I said two papers. And then what we do is we can run the algorithm, and then we can produce a PPT state sigma 0, such that this upper bound is exactly equal to this, and this definitely upper bound, right? Because here we only choose a very specific state. And then we can achieve our goal just to show this chair of equalities. So that is something very straightforward. So the problem is this proof is not totally a completely analytical proof, which we are which we all prefer, right? It's not, but it's very convincing because everything once you have this idea, and then you can just calculate this only this part you need the numerical calculation. But we should trust the computer because if you run again and again, it produces the same result, right? So this details, this class of state, and this some analytical detail. So, but what we do is eventually for this class of state, what we can show is there is a gap. So we can produce the gap to show that this response is not additive. Okay, so response is not additive. So how this could be useful, right? So actually this has some application because as we said, the response is the best upper bound of this entanglement distillation. But now it's not additive. So what we can do is we can use this property to define the regularization of this response. And then this regularization should be a better upper bound for this entanglement distillation. So this is the application. Okay. So what we do is we can introduce a regularization, and then what we have is this better upper bound. But as happened in many cases, Hayashi already have this idea. Hayashi, even before he knows this response is additive or not, he already introduced the regularization. And so our result just confirmed this regularization is strictly better than the response. So, okay. And the upper problem it's very straight. It's just it's just like a random work. I don't even push it. Okay, but yeah. So I don't know why it doesn't show this part. It's very strange. Yeah, but I hope you can see it, right? Because this here we come this open problem list URL. So the open question is relevant open question is this PPT manipulation or entanglement is reversible? Okay, this is the 20th open problem in this winners list. Okay, and so what we say is whether this EC rule equal to ED rule for any bipartite state. This is the open problem. This is and another thing is is the regularization of relative entropy of entanglement equal to the regularization of response? Because we already proved that response is not equal to this regularization of this entropy or relative entropy. But how about if we take the regularization of this response? So whether we have this regularization of response equal to this regularization of this relative entropy, okay? So these are two upper problems. Okay, and these two upper problems are actually, the answer is negative. The answer is no, actually. So the the key idea we have is we have a new SDP Noah bond for the regularized relative entropy of entanglement. Okay. So suppose the state we are studying is rho AB, and then PAB is a projection over the support. Then we can find a Noah bond for this regularization of this relative entropy. Okay. So yeah, and this eta PAB is given by this SDP. So T is a real number, actually positive real number, and YAB is another operator variable. And then we need to have this T and YAB satisfy this constraint. And this is a very simple SDP, so it can be calculated very easily. And then we can show this is provide a Noah bond for this relative entropy. Okay. So the key observation for prove this is to use this property. So what we have is for any state rho and sigma, so the relative entropy between them is always Noah bounded by this trace PAB sigma, take the minus log. So this property is actually a corollary of this this relative entropy has a property. If you take the CPTB map over rho and sigma, then it's always always can non-increasing. So we use this property. It's monotone. So under this CPTB map, so we use this property, we can show that we have this property, and then here we take the minimization over all state PPT state sigma. Then we can have this one will nudge the this property, this quantity. So the point here is if you take this sigma in PPT state, then we know this one can be calculated by a SDP problem. But this SDP, unfortunately, its property is not very nice. For example, it's not multiplicative under this test product. So what we do is we just need to further renex the interbit, and then we have this SDP. Here we also use the duality of this SDP. So it's but anyway, I mean this all very routine. We can renex this one into this number. So this number has many interesting properties which I cannot detail here. But one important property is that it's multiplicative. So people will ask why you always require this property to be multiplicative. There is a very simple answer for this. Only when you have some multiplicative quantity, then you can use it for this asymptotic case. Because if you take many copies, then if it's multiplicative, then you can just take the power of this one shot, right? Otherwise, we can do nothing, right? So this is why we need to have this. This is the Noah bound for the one shot. But then if you take the n copies here, you still have the same, same Noah bound. But here you have just n times, because it's multiplicative. Okay, this is a reason we need to have this multiplicative quantity. Okay, so okay, I go very fast because today I try to be fast because I always can't finish this. So maybe we have time to discuss the examples. Okay, so I give you some example because the examples are very, very simple. If we just consider the uniform mixture of two states, these two states are 3 by 3, but it's on this anti-symmetric space. So here you see this is V1 is just the 0, 1 minus 1, 0. So this is the anti-symmetric state. And also we have another state 0, 2 minus 2, 0. So this clearly very simple state. And then we can have, for this very simple state, we can calculate this, this logarithmic negativity. And then we find it's just equal to log 2, 1 plus 1 over square root of 2. So this is strictly nested 1. But the upper bound we have for the relative entropy is actually equal to 1. this is also the entanglement cost, because you can say, because this is a mixture of two by two maximum entanglement states, so you only need to use one EPR state to prepare this mixed state, right, by LOCC protocol. So the entanglement cost is actually not more than 1, but we have this lower bound is equal to 1, so they have to all equal to 1. So this is the case. You can see the regularization of this relative entropy is strictly nudge the response, and also strictly nudge this entanglement destination. So this already provides a separation between the entanglement destination and the entanglement of cost, or entanglement of dilution. So this example can be generalized to any Rec2 mixed state, supporting on this 3 by 3 anti-symmetric subspace. So for any this kind of states, you can always show that we have this separation between ED and EC. So here we have this a very standard form of this 2 by 2. Rec2 mixed state supporting on this 3 by 3 anti-symmetric state. So we can write it in this form. So one state, you can always choose it as a 0, 1 minus 1, 0. And then another state, it always can choose as A2 minus 2A. So A is some state. So we can always write it in this form. And then we can show that ED is actually strictly nested 1 because we use this logarithmic negativity as the upper bound. And then we have ED strictly nested 1. But as we just proved, we can show that for this kind of state, we only need one EPR state to prepare it. So the entanglement cost is is just 1, actually 1 just equal to 1 EBIT. So we have this separation. Okay. So yeah, actually I finished early. Yeah, it's finished. Yeah. So any question, welcome. Yeah. Yeah, Aaron, please.
Have you looked into how this bound does for various random states? It reminds me of a little bit of how Ashley Montanaro was looking at a different thing which is not multiplicative, which is the minimum S infinity output entropy. And he could show it was weakly multiplicative for random channels because he had this exactly, this easy compute multiplicative bound on it. I wonder if random you might be able to show something similar.
Actually, the tactic we use here have one shortcoming, because you can say we can only apply this tactic for some state that is not 4 rank, because it is 4 rank. Then the bound we have is trivial. For example, this is eta p, right? That will be trivial, just 0. So we don't have anything. So it's applied to some non-4 rank state. So clearly, if you have a random state, then it's 4 rank.
Well, you can pick it if you want to not be 4 rank.
Then yeah, that's a next experiment we need to do. Yeah, we need to do the test. Yeah, thank you.